Okay, in this last video associated with Chapter 6, we're going to look at free radical additions to alkenes. In this first reaction, we're looking at reversing the regiochemistry of HBr addition by adding peroxides to the reaction mixture. And the big deal here is that when you add peroxides, you change the mechanism from electrophilic addition, like without peroxides, to it's now a free radical reaction. Okay? Just one comment, however, about this reaction before we look at it. This reaction is hardly ever used. The only reason I'm presenting it is because it might appear on the MCAT or some other standardized exam. What really, the people who write textbooks and the people that write these standardized exams need to get together, need to look in the literature, see how commonly this reaction is used, and they would realize nobody uses it, then they would dump it. So this reaction really needs to be dumped from the curriculum. It's not important, but I'm going to present it anyway because somebody else in your life might think that it is. Okay, a good example of a peroxide is benzoyl peroxide. This compound right here, which is also the active ingredient in Clearasil. Okay, all right, and these benzene rings here, we're going to give the abbreviation pH to symbolize the abbreviation for the benzene ring. So this benzoyl peroxide is going to be represented as the compound right here. Okay, so when you have the peroxide present, mild heating will cause the oxygen-oxygen bond of the peroxide, which is not very strong, to just break. Okay, so mild heating causes the oxygen-oxygen bond to rupture, and you get this radical here known as a benzoyl radical. This is the true initiation step, but benzoyl peroxide is really just a catalyst to get the reaction going, and doesn't really appear in the propagation. So I need to have this other step between the actual propagation and the initiation. I've invented the term pseudo-initiation to refer to what this step here is. But what we're going to do is we're going to take the benzoyl radical, HBr. We're going to transfer a hydrogen atom off of HBr onto here to make benzoic acid. And the bromine radical. And this is what's going to be involved in the actual propagation. All right, so the bromine radical is going to add to the double bond. Okay, and this double bond, if you look in the resonance chapter, we know that these two electrons here are actually bonded, but there are two electrons, one at each carbon, so we can actually react one electron at a time with the system. And this can give us either of two radicals. If we add bromine to the end, we get the secondary radical, and if we add bromine to the middle, we get the primary radical, which of course is less stable. And this is the way the reaction is going to go. It's going to go through the more stable radical. Okay. All right. So once we make this radical, it's now going to abstract a hydrogen off of HBr, just like benzoyl radical did over here, but now it's with this radical. Okay, and this is going to, again, abstract the hydrogen from HBr. This is going to make the product, and the bromine is going to re-enter the cycle right here. This reaction is not really all that clean. It's hard to get this reaction to go 100% through the free radical pathway. The electrophilic pathway is competing with it to some extent. So people just don't, when people really need primary halides from alkenes, we're going to see that they don't use this reaction. We'll discuss that process when we get to chapter 8. We'll see a much better way. Okay, a far more useful reaction involving free radicals and alkenes is polymerization. So if we take one other comment, I've just used benzoyl peroxide as the initiator here. Any peroxide molecule could serve technically as the initiator. It just has to have an OO bond. The benzoyl peroxide is one of the cheapest and the most stable free radicals, so you'll see it used probably more than any other free radical initiator. Okay, so if we treat ethylene with benzoyl peroxide and heat, what we're going to find is that we turn our ethylene molecule into many, many repeating ethylene molecules. I put 10,000 or so here to signify that there are a lot of these molecules. If this truly has 10,000 of these units, that means that these two ends of the molecule are really an insignificant part, part of the molecule. And really, when people are representing this molecule, polyethylene, they usually represent it this way, where we just take the simplest repeating unit, which corresponds to the basic units, carbon units that we have in ethylene, and just write in parentheses that there's a very large number of these units that have gotten together to make this compound. Okay. All right, so this is really a better indication of the structure because, again, if there's 10,000 of these, there's only 2 of these, and therefore they're not a huge percentage of the molecule. All right, how does this reaction go? We break the OO bond like we did before. We're going to add this to the alkene to generate a new radical right here. Okay, this radical, as long as we have lots and lots of ethylene around, can react with another molecule of ethylene. I could, if you really wanted to see this, I could do this same thing 9,998 more times, but that's not really a good use of video time, so let's just assume that that process is going to happen over and over and over again until we build up a very large molecule. Okay, ethylene's symmetrical. Let's look at what happens if we have an unsymmetrical compound like propylene. Okay, propylene, if subjected to the same conditions, also makes a polymer, but notice how the methyl group perfectly alternates in this structure here. Okay, we have a CH2 followed by carbon with a methyl, followed by a CH2 and a carbon with a methyl, CH2 and a carbon with a methyl. This pattern repeats itself quite faithfully throughout the structure of this compound. We can represent it basically as this repeating unit right here. Okay, so how does polypropylene achieve that structure? The polymerization reaction is exactly the same as the other one, okay? Except that when we add this one, we have a choice of 2 radicals. This is a secondary radical. When we add it to the end, and we generate the radical at the secondary position, we can add the oxygen to the middle, and this gives us a primary reaction radical. This is less likely to occur, so we don't see the reaction going by that pathway. Okay, it can react with another one, and again, it has a choice to make a secondary radical or a primary radical, and it chooses to make the secondary radical, and that's how we get the methyl groups in alternating units. Okay, many monosubstituted and disubstituted alkenes, or mono and 1,1 disubstituted alkenes, have been successfully subjected to these polymerization conditions. Okay, so there's polypropylene. This is the basis of the DuPont Stainmaster carpet. You can sort of see why it would be a good stain-resistant carpet. Nothing would have very much affinity for this, since the only intermolecular forces it would have for any stain molecules would be van der Waals forces, and they're not very strong. Turns out that free radical polymerization is messy for another reason. We'll talk about that when we talk about stereochemistry and look at how conditions to polymerize it with control of stereochemistry have actually led to this being a far more useful material. Okay, polystyrene. Okay, we probably associate or we're familiar with polystyrene, right? It's kind of brittle compared to polyethylene and polypropylene. Okay. This is the clear plastic cups are made of polystyrene, and if you blow air through the system while the polymerization is occurring, you get styrofoam. Okay, they're both basically the same thing. It's just that with styrofoam, the matrix is filled with air as well as the polymer support. Okay, polystyrene has a lot of sp2 carbons in it, so what we can see is that it's a little more rigid. It's the lack of flexibility translates to the overall structure, and because of the presence of the sp2 carbons, it's not as easy to bend, or it breaks a little. It's not as flexible as polyethylene. Okay, polyvinyl chloride is what you get when you take this molecule, vinyl chloride. This molecule, by the way, is styrene. Okay, and you polymerize vinyl chloride and you get polyvinyl chloride, and this is of course the material that's used in a lot of plumbing and raincoats and various other plastic materials. I think siding for your house is also made of polyvinyl chloride. Okay, this molecule, methyl methacrylate, is a very important polymer. Polymethyl methacrylate is actually a very hard material, and it's what plexiglass and dental fillings are made of. Of course, you'd want your dental fillings to be very hard, right? You don't want them to change their shape just because you scrunch on a piece of ice or something like that. This molecule here is acrylonitrile, and when it's subjected to the polymerization process, you get polyacrylonitrile, or Orlon. This molecule, tetrafluoroethylene, is actually we should be able to appreciate its design because the CF bonds are very strong. So people wanted a no-stick frying pan, so they actually have to have a polymer that's sturdy at very high temperatures. So the idea here is that the much stronger CF bonds replace the weaker CH bonds, and you get a plastic material that you can heat to a much higher temperature. This should be called polytetrafluoroethylene, but for every chemist making a new material, there's another person in marketing trying to design a catchy name, so this is where Teflon comes from. Okay, you can sort of see the elements tetrafluoroethylene in the name Teflon. Okay, so these plastic materials have largely replaced a lot of the natural materials. The addition polymers that you see here, one of their advantages is that they have much higher environmental stability than comparable natural materials. That might also be their downfall. Supposedly a polyethylene trash bag can last in a landfill for 10,000 years or something like that. It's so strong, or it's so inert to any chemical process, but people are trying to build in structural features that'll allow these trash bags to degrade over time. So polyethylene is just too good. Okay, so here's a problem for you. Look at the structure of each polymer and see if you can make a guess as to what would be the monitor that gives rise to it. Pause the video, do it, then restart the video, and I'm going to go through it. Okay, this type of problem here, really, what you want to think about is the fact that you're going to have these two sigma bonds that are continuing the chain are going to be gone, and you're basically going to end up with a pi bond right there, and that's going to be common to every one of these. Okay, so this is the polymer of 2-chloroacrylonitrile right here. We'll say a little benzoyl peroxide. We'll turn that compound into that. This is the polymer of 2-methyl-1-propene. Okay, we also saw how you could make this polymer by electrophilic addition as well earlier, right? The polymer that you see here, okay, this one comes from the cyclopropene, and of course this would be actually a very favorable process, right? Because here we have sp2 carbons in a small ring, and here when we get to the product we only have sp3 carbons, as you can see right there. Okay? Alright, so that would be a very favorable polymerization. Okay, the rest of what we're going to look at is just, for the most part, features. We're going to look at the end here in this chapter about how to string two reactions together. But let's just look at a really good application that really tells us how the processes that we uncovered in chapters 5 and 6 are really important. I can think of no clearer example of that than cholesterol biosynthesis. Okay, so cholesterol in the body is synthesized from a molecule called squalene. Okay, so squalene undergoes a biological oxidation to squalene oxide. Okay, and then there's an enzyme that's going to protonate this. We're going to open it to make a tertiary carbocation, and that gives us this structure right here. Okay, this is now going to add to the alkene in the molecule to make another carbocation. This is going to add again to generate another carbocation. It's going to add yet again. I think I've repeated the structure again. Yeah, okay. It's going to add to the double bond yet again. Here's kind of the step that's probably the hardest to understand. Why do you get a secondary carbocation instead of the tertiary carbocation? I guess the enzyme is kind of scrunching this molecule into a shape where it just gets carbons closer, and that overrides the carbocation stability issue. But after this point, we're also generating tertiary carbocations, so that's going to add there. We get now another tertiary carbocation. This does a 1,2 hydrogen shift. To make the next compound, I'm going to repeat the structure of this one here. Okay. It's going to do another 1,2 hydrogen shift. Okay. It's going to do a 1,2 methyl shift. Okay. We get that. It's going to do another 1,2 methyl shift. And we get this carbocation. And let's see, what is it going to do? It's going to lose the hydrogen here to make the alkene. And this is a a steroid called lanosterol, which undergoes biological degradation further to provide cholesterol. Okay, we wouldn't put this on the exam, but it's important to realize that carbocation rearrangements are really very important in not only in chemical systems but in biological systems as well. So understanding carbocation rearrangements, it's actually very important for understanding how natural products are made in biological systems. Okay. All right, this last topic we're going to look at is called multi-step organic synthesis. And this is a feature that gets to be a bigger and bigger part of each chapter as we acquire more reactions under our belts, okay? As we become smarter, as we know more and more about organic chemistry, we have more and more reactions that we could use. All right, so here's a multi-step problem. How do you convert that into that? Well, there's no one-step method for doing that. That has never been covered in class, and I don't know of one, even with 100+ years history of organic chemistry. I don't think a one-step method to do this transformation has ever been invented. Okay, so how do we approach these problems where you have to use more than one reaction to turn a starting material into a product? This is what organic chemists get paid for doing in the real world. So we love our synthesis problems. All right, so you have to start thinking at it on a deep level here. Okay, so we're just ask ourselves, how does one prepare a secondary alcohol? Okay, so if it's a discussion, of course, there'd be a friend. All right, okay, so there's a myriad of methods. However, you should focus on their preparation from alkenes, the theme of chapter 6. Okay, so we're going to have a little bit of guidance here for you in that we're probably going to emphasize reactions that we're talking about in the chapter that we're looking at. So this is the alkene chapter. All right, so let's think about how we can use alkenes to interconvert these two compounds. All right, so we know that this product, this is our what we call our target molecule. Okay, that it comes from an alkene. Okay, and it could come from one of two alkenes. It could come from the alkene that we have here on the left, or it could come from the alkene over here, right? But we know that if we use the alkene on the left, we could selectively add OH to the less substituted carbon using that boron stuff, right? But if we had this alkene, the OH could add to either one of those carbons, and we don't have any, the degree of substitution of those two carbons is the same. They're both they're both alkene carbons with one hydrogen on them, so there's no difference in the substitution pattern there. So we're going to have to use this as our precursor compound. Let's just over here, I'll draw again what is our designated starting material, so we don't forget what that is. Okay, so somehow or another we have to think about, as we identify legitimate precursor compounds, we also have to think about how they relate to our ultimate starting material. And if you look at this compound here and this compound here, of course they're related by a dehydration process, right? Okay. Yes, by dehydration. All right. So here's the answer. It's a two-step synthesis. Okay? We treat it with sulfuric acid. This gives us the alkene. The alkene that we get, we treat it with under the hydroboration conditions, and that gives us the alcohol in the place where we're asked to put it. Okay, let's do another problem. This takes 3 steps. How do you convert that alkene into that epoxide? Okay, try to do this on your own. Do the best you can. Pause the video, but I'm going to go through the solution right now. Okay, at this point, you're very limited. You haven't had that many reactions, so that can make these problems a lot simpler. You have to count on the person asking you the question to be a reasonable person asking you questions that you've been trained how to answer. So let's just assume that that's the case. All right, you only know one reaction that makes an epoxide, right? An epoxide has to come from an alkene. Okay. All right, so somehow or another I've messed up the animation. Sorry about that. Okay. The only way we're going to be able to make this epoxide is by treating that alkene with a peroxy acid. Okay? Now we want to think about how do we make that particular alkene. That alkene, of course, is made by taking a bromide or an alcohol and then doing either a dehydrohalogenation or a dehydration. Either of those gives us the compound right here. All right, and if you think about how do those compounds relate to the product that you see there? Of course, we can add HBr or mercuric acetate or water sulfuric acid perhaps to make either of those compounds, and then after that they're going to be dehydrated. Okay, and yeah, so good job there. This yeah, sorry about the animation here. It would have been so great if Peter Griffin had appeared there at the very end of this, but I'll fix that at some point. Okay. All right, so this is the synthesis. The best way is to add HBr, dehydrohalogenate, and make the epoxide. Okay, these synthesis problems become, they're like the Kevin Bacon game that you might have heard about, linking movie stars through films that they've starred in together. Organic synthesis is the same general idea. Okay, and it actually gets to be fun and challenging. All right, so right now, it's good to understand how to do this now while we don't have that many reactions. And then it slowly gets a little bit more complicated, but it won't be overwhelming. Okay, so try to get good at synthesis problems. Try to do a fair number of them while we haven't had that many of them so that you get the art of organic synthesis down, and then you can solve harder problems as we acquire more reaction knowledge. Okay, this is the last slide here. Anytime that there's recent Nobel Prizes that get awarded for something, I like to talk about them. Okay, so if we look at recent Nobel Prizes for alkene chemistry, 2005 we had a Nobel Prize for this reaction here, which basically isomerizes the ends of an alkene, and this is called olefin metathesis. Okay, so this catalyst here catalyzes it. Okay, and this produces all possible combinations of R1 and R2 on the alkene, 2 R1s, 2 R2s, ethylene. In some cases, this reaction that seems like it's messy in here can actually be very selective. So in this process here, It's called ring closing metathesis. It's driven by the formation of a nice stable 5 or 6 membered ring and the formation of a gaseous byproduct which goes out of the system and uses Le Chatelier's principle to drive the reaction to equilibrium. And this last one here, called ring opening metathesis polymerization. Okay, we open the ring system, and this actually relieves ring strain. This is kind of a small ring with sp2 carbons in it, and when we break the ring and make this compound here, this also has the abbreviation ROMP. There's a tremendous thermodynamic driving force for this process, and this is actually a new way to make polymeric substances. Okay, so this sort of ends chapter 6 right here, and we'll look at that. So anyway, the next chapters will be chapter 7. We're going to go back and look at a lot of the reactions in chapter 6 and chapter 7, learning some of the new things that we learn about stereochemistry in chapter 7. Okay.